Continuing to our Chapter 3, Challenges and Solutions in Developing Optimized and High Efficiency Optoelectronic Devices with Solar Cells. As a topic overview, we're going to start with the generations from first to the third generation, and then we're going to moving on for the next generation. So as a summary, based on our previous topics, the first generation is the wafer-based solar cells such as silicons, and the second generation is the thin film solar cells TFT, and the third generation is including organic solar cells, and so on. And then we're going to move on with the tandem solar cells and examples. The first one is the silicon solar cell. There are three types of silicon solar cell. The first one giving the monocrystalline, second one is polycrystalline, and the third one is amorphous silicon. So this is an example for the typical structure of a silicon solar cell, start with glass, anode, N-type silicon, and P-type silicon, and also cathode. For monocrystalline solar cells, it is made from a single crystal of silicon. It can be synthesized by Sourlaski CZ process. Standard process propagation of high-quality silicon process of wafers, including the production chamber, where this is the process of melting silicon up to 1500 degrees C for melting the raw silicon in to be as a crucible. And then the impurity atoms were added, either P-type or N-type. The silicon was melted and in a rotating shaft with a seed crystal mounted, dipped and also drawn upward. This process requires a controlling of the temperature gradient, pulling rate, and also the rotation speed. After that, the sample was cut into small slices from ingots. However, this process of single crystalline fabrication is very high and also have a highest reported efficiency. For polycrystalline solar cell, it consists of a recrystallized silicon. This can be cut into a very thin wafers. This process requires a very low cost of manufacturing. For better performance, these types of silicon or polycrystalline needs a more rooftop space. The efficiency range is comparatively lower than the silicon single crystalline solar cell. Amorphous silicon. This type of silicon is a thin layer of silicon atoms, not crystalline layer, containing several layers forming a specific crystalline structure. This type of silicon has a capability to absorb light at a thin layer, termed as a thin film amorphous silicon solar cells. It has a better performance at high temperatures, requires twice the rooftop space for similar output power as silicon crystalline. These are a typical commercialization process of crystalline silicon solar cells. So as you can see here, you start off with a silica to low purity silicon and high purity silicon. For a monocrystalline type or single crystalline type, start off with a CZ crystallization and then followed with the slicing of the silicon and turn it into a wafer, of course to the cell, and to a complete module. The second one is the polycrystalline type. As you can see here, these types of silicon scrap from the monocrystalline type silicon crystallization is put into here with a crucible, and then it was formed into an ingot block. Then we can slice the wafer, turn it into a wafer, and then followed with a cell and also a complete modules. So to summarize, for the silicon crystalline solar cells, it has a high production cost, high material usage, high installation cost. However, the emerging technologies can enable the production of flexible solar cells, reduces the installation costs, including nanostructured silicon solar cells, however, are much more attractive because of the excellent anti-reflection properties. These properties is unique, which include multiple internal reflections, strong light trapping, resulting in non-zero optical reflection, and of course it has a high efficiency. These first generation solar cells are stable operation. However, the efficiency decreases at high temperatures or under a mechanical loads. The limitations for The single crystalline solar cells includes photons energy hits the solar cell, thus reduce the band gap, resulting in the light cannot be converted into electricity and lost. The incoming photons energy increases the band gap, which resulting in the excess energy that is lost as heat. The Fermi levels or N or P type silicon remains inside the gap. Thus, the open circuit voltage is smaller than the band gap. Second generation solar cells, TFT solar cells, thin film solar cells, TFSC or TFPV. This type of solar cells consists of two heterojunction layers that is squeezed in between two layer contacts. The chalcopyrite structure of copper indium gallium diselenide CIGS and CDTE telluride thin film is thoroughly researched. The highest efficiency of these types of solar cells is around 22.6% and 22.1% respectively. The typical structure of this solar cell is including glass anode N-type semiconductor, intrinsic P-type N-type semiconductor, intrinsic another, and also P-type semiconductor, and finally with the cathode. So this consists, for example, for the one junction of PIN or two junctions of PINs. Copper zinc tin sulfide selenide CZTSSC has the higher efficiency of 12.6%. A substitute for CIGS is necessary to reduce the cost utilization of the abundant, non-toxic material with rare metal-free absorber layer. CZTSSC absorbers has a unique property such as high efficiency due to reduced energy losses. It can harvest more photons from the sun. The actual efficiency in comparison with silicon are still lagging, however. These types of solar cells exhibits high solar absorption coefficient by layer thickness of 2.5 micron, for example, up to 170 to 250 in comparison for the solar cell. Thin film solar cells advantages is including low production cost, mechanical stability, and the possible to fabricate transparent solar cells. The advantages also includes a simple mass production, cheaper to manufacture than the crystalline-based solar cell. It is homogeneous, which is so appealing. The flexibility enabled, so this can lead to a new potential applications. It has a less impact in performance in a high temperature, also shading. In a situation where space is not an issue, this type of solar cells is relevant. However, the disadvantages are it is not very useful in the most residential situations, require a substantial amount of space. Monocrystalline solar cell produce 4 times the amount of electricity as thin film solar cell panels for the same amount of space. Low space efficiency, the cost of PV equipment, for example the structures and the cables, will increase. However, also this type of solar cell degrade faster than mono and polycrystalline solar cells, typically come with a shorter warranty. Third generation of solar cells, polymer-based. This structure of solar cell consists of 1 and 2 layer or a mixed type. One layer, organic polymer sandwich between two electrodes with high and low work function. These types of solar cell can absorb the light with the formation of excitons in the polymer layer and dissociation of these quasi-particles into electrons and holes under the action of electrode potentials. These two layers of cells with different polymer layers. One is donor layer and the other is the acceptor layer. So this is an example of the structure of polymer-based solar cell. Transparent conductive layer, hole injection layer and N polymer layer, P polymer layer and N polymer layer, and also the electron injection layer and the electrode AG. Two-layer cells provides more efficient charge separation than the one-layer cells. In a mixed type, the role of electron donors by conjugated polymers, fullerenes, as an electron acceptors. To improve the efficiency of this type of systems, one should extract a photo-generated charge carriers from the active layer. This can be done using a so-called electron and hole injection layers such as EIL and HIL for the negative and positive charge carriers respectively. These disadvantages of these types of solar cells includes a low stability. This is due to the high sensitivity to oxidation and has a low light absorbance. These are the most famous and the most thoroughly researched polymer-based solar cells. It is P.PSS with silicon crystalline heterojunction solar cells. These are the chemical structure for these types of P.PSS. This consists of two ionomers. The first one is P dot. One ionomer is the conjugated hydrophobic and conductive polymer, which transport the positive charges. Another ionomer is the hydrophilic and insulating PSS chain, which transport negative charge. Based on the spectroscopic ellipsometry, it is revealed that the average carrier concentration for this modified P.PSS is 10 to the power of 20 to 21 over cubic centimeter. Thus, P.PSS polymer has a metal-like properties. The Schottky junction is frequently observed at the metal semiconductor junction, and there are many studies which consider N-type silicon P.PSS interface as Schottky-like junction. In addition, P.PSS shows a optical anisotropic behavior, uniaxial with the optic axis parallel to the normal surface, and large HOMO-LUMO energy difference, approximately around 5.05 eV. The fabrication process for these types of solar cell is including spin coating, electrospray, chemical mist deposition, screen printing, and inkjet. These are the example of a typical structure of P.PSS silicon crystalline heterojunction solar cell. The evolution of efficiency of the P.PSS crystalline silicon heterojunction solar cell is shown in this figure. During the emergence of the P.PSS heterojunction solar cell in 2011, the efficiency of the cells was 10.1%. The power conversion efficiency of this solar cell was further improved up to 10.8 and until 13.3% with a silicon substrate by increasing the conductivity and uniformity of the P.PSS films by employing a different type of solvents, for example MEOH, e.g. mixed of both, or DMSO. Also with the adjusting the solution concentration and thickness of the P.PSS as well as the silicon substrate itself. There are a lot of design modifications, like the modification of PSS with the addition of nanomaterials, light trapping, front intermediate and back interface engineering, metal nanowire, buried metal electrode, and dopant-free back surface field BSF layer, which has been employed for further improvement of the efficiency of these types of solar cells. The efficiency was rather improved up to 15.4% by introducing the AR coating without the additional light management such as texturing or pillar system. In 2016, the efficiency of solar cell was reported up to 15.9%. The efficiency of the solution process P.PSS silicon solar cell reached up to 17.34%. This was done in 2018 actually, with a structural, electrical, and interfacial engineering simultaneously. Most recent PWSS, the efficiency was increased up to over 20% with a back-feeder structure in textured silicon substrate, which is actually a silicon p-n junction, where PWSS was used as a p plus back surface fill layer BSF, and which also requires conventional high temperature processing steps in addition to the low temperature solution process. Therefore, it can be concluded that after a decade of emergence of efficiency of PWSS, silicon solar cell has reached nearly 20%, well below the efficiency of the existing silicon solar cells. Therefore, it seems there is a need for a breakthrough to reach the efficiency of the solution process with a solar cell crystalline silicon for that to beat the reported silicon solar cell. P.PSS silicon crystalline heterojunction solar cell challenges includes stability. It is because this type of solar cell is very acidic with a pH of 1.8, and also it is hygroscopic in nature, which means that it tends to absorb moisture from the air naturally. Thus, the performance of these devices deteriorates due to the oxidation itself. This moisture came from the air of the sulfonate group in the PSS matrix. As a solution, the first one is the introduction of higher open circuit voltage here. And also the second one is the introduction of anti-reflection coating layer, such as this, which using AR coating of molybdenum oxide or a amorphous TiO2, or even a strontium titanate. Efficiency limits, light trapping and Lambertian limit. Optical thickness is determined by a trade-off between the competing needs of high optical absorption, which require a thicker absorbing layer, and of a efficient carrier collection, best achieved by a thin silicon layer. Efficiency limits can be calculated by solving the transport equations in the assumption of optimal Lambertian light trapping. For example, assuming 100% carrier collection, the short circuit current density of a solar cell is given by the density of photo-generated carriers as this formula, whereas the AE is the absorbance of the photoactive layer, for example, the spectrally resolved absorption probability, where AM 1.5 flux is the photon flux corresponding to the AM 1.5 G solar spectrum, and for the thickness D and an absorption coefficient alpha E, neglecting the reflection losses. That is all from me today. Thank you and have a good day.